our final speaker here before lunch, who is Dr. Pontus Brandt. He has a PhD in space plasma physics from the Swedish Institute of Space Physics in Kiruna, Sweden. He's currently a senior professional staff scientist at Johns Hopkins Applied Physics Laboratory.
So, I'm Pontus Brandt. I hate to stand between you and lunch and the food, so I'll try to make this fast. From APL, as I said before, we're the guys who are doing the New Horizons mission and launching Solar Probe soon. I work with Ralph McNutt, Michael Paul, Mike Rishkevich, he's our boss on the block. I also work with Tom Kermedius on this. All right, so I am here to talk to you about how do we do this today? You know, for a minute, forget about solar sails, forget about laser propulsion. What can we do today? So we've been discussing interstellar probes for, 60 years now, right? Some things have happened, of course. So first, a little definition here. An interstellar probe, or a precursor, historically, it's been sort of out to 200 AU within 30 years or so, but we really need to talk about 1,000 AU within about 50 years or so. It would be, at least to me, the boldest undertaking in space exploration. So we have a long line of history here. It started even before this with names like the Deep Space Probe and the Ultraplanetary Probe and things like this, Jupiter Galactic Probe. None of these are actually names of mission. They morphed into other missions. But then we have other lines of known missions. We have Pioneer, we have Voyager in '77, and then, of course, New Horizons. And believe it or not, Solar Probe is very related to an interstellar probe mission because of the Oberth maneuver. That will be, Parker Solar Probe will be launched next year. This is a little bit about the history here. It started already in the 60s when they talked about an outer solar system probe to be aimed away from the sun. And then in '65, Eugene Parker, he is still alive, and I met him actually 2 days ago. And he started advocating for a mission to this heliospheric boundary region to really explore the boundaries into the local interstellar medium. Then '77, Voyager 1 launch, and now as of last week, Voyager 1 is about at 139.9 and at an asymptotic speed of about 3.6 AU per year. So that's the velocity, that's the escape velocity we're at right now. As any other missions that I've been involved in, everything is science-driven. All the missions are science-driven. The one closest to my heart, and also historically here, is our astrosphere, or the heliosphere. You've probably seen the abundance, well, it's not maybe abundance, but numerous astrospheres being observed in the UV by Hubble Space Telescope. These are stars of various ages that show how they build up bow shocks and tails as they plow through their interstellar medium. And in fact, none of these are like our own heliosphere because we cannot see our own heliosphere in UV. We can see it with other methods, such as this one, which is called ENA imaging. So that brings about that we don't really understand at all what our heliosphere really looks like. And if you look back at this, these are other astrospheres that are harboring other exoplanetary systems that may harbor life. So we need to make that sort of connection happening here. And of course, these are also new astrophysical plasma conditions that we need to get out and explore and understand. Next big science target was brought on by New Horizons, and I know probably all of you have looked at the images, and maybe some of you, just like me, before they launched that mission, I argued, well, guys, you're spending this much money for a 4-hour flyby. Are you nuts? But look at the images. They were totally worth it. And we have a whole host of other KBOs out there. KBOs are not just gravel circulating around there. This one here is just one that we have targeted, and that's the dwarf planet Quaoar. It's located about 40 to 50 AU out in the nose direction of the heliosphere, so that conveniently lines up with that physics. It's very interesting because it's sort of bordering on those, how should I say, not airless, but atmospheric-less bodies versus the bodies that actually have atmosphere. So we do believe that this is in the last stages of losing its atmosphere. Next one, this is a pretty recent image from back in 2009, a discovery of a young planetary system, very young star in the middle, and this is accumulated from several different observations, I believe. But it shows spiral arms in irregular fashion. And it turns out that this is most likely the manifestation of planetary evolution going on in that young exoplanetary system. And sitting inside our own bubble and the zodiacal dust cloud, we have no clue what that dust distribution looks like. We don't know what our circumsolar disk looks like. So if we pop outside that bubble and take a look at it in very simplistic terms, that's a huge science driver for a mission like this. Won't dwell on this. This could be truly and potentially groundbreaking. There are maybe some engineering details to work out, but we'll save that for this afternoon. Now to my little, starting to become my little pet favorite here, I guess. Planet 9. Number 1, we don't even know if it exists, right? So this was Konstantin Batygin and Michael Brown who announced this hypothesis, I would say. So it came about as they looked at the clustering of KBO. So if you look at the clustering and the argument of perihelion, it actually clusters around. It's not a lot of data points here, but it's statistically significant. One of the solutions is a big planet, about 10 times the mass of Earth. So this is nothing like Pluto or Quasar. This is pretty big. Slightly inclined, the solutions suggest a slightly inclined with a apoapsis of about 1100 AU. There's a range to it, and a periapsis of 200 AU. That's sort of within reach. That would be a huge target if it exists. So that's something we're definitely keeping our eyes on. All right, so let's get into the technical stuff and try to be realistic here. I hope I won't disappoint you too much. Payload, this is my only slide on payload. Obviously, there will be an interstellar medium and heliospheric suite of particle, plasma, magnetic field instrumentation. We call this also an ENA camera to take that snapshot back at our own astrosphere. So it's a particle camera, dust detector to get that spatial, the radial spatial distribution, also size distribution of dust as you go out. And then, of course, very importantly, imaging systems. There have been imaging systems that people are looking at. It's been reported in the KISS report from the KISS study. So we have optical and infrared. Can they be combined? There have been proposals to do that. The optical would, of course, do the flyby imaging of KBOs. Of course, the trade-off there is that the faster you fly, the less photons you collect, and the more smear. This one here is from Bach et al. This is a sort of integrated suite of optical and IR instruments in the same package. All right. Flowing down from science targets and science requirement, we come to mission requirements, and that's how we build missions that fly eventually. So historically, as I said, it's been 200 AU in about 30 years. But we do need to extend that discussion and those trade-off studies to 1,000 AU within 50 years because of the science target I just explained. And also that this would be much more impactful if we want to sell it. So that's tremendously important to remember this. We need to consider all possible missions that launch between now and 2015. I don't think that's really changed. What we want to do is look at existing launch hardware. We don't want to wait for new technology, no in-space assembly. That will complicate matters too much. Trivial. We got to launch to escape velocities, of course, and keep the technology and hardware development to a minimum. And this one, not to be underestimated, we need to use that adequate margin philosophy to achieve that lifetime reliability. So the folks of you who have been involved in missions, we're burdened with these margins on margins on margins, and they just pile up. So if we were to have those margins back in the Voyager days, I'm not sure if we would have flown that mission, to be honest. So somehow we got to get around that. Okay, so let's get back into the trade-off studies that we've done here. So the first one, I think Slava already showed, and that's direct launch into a Jupiter gravity assist. No sun involved here. Okay. And what we do is to take the best of the best, and basically, as Ralph McNutt would put it, stack that sucker up. So this is the SLS-1B block. Up here we have another stage of the cryogenic stage, the interim cryogenic stage. We also assume the Castor 30XL, and then on top of that itty bitty piece is the 450-gram model spacecraft based on New Horizons. And this also sits on top of a Star 48 solid rocket engine. I forgot to put that there, but that's tremendously important. And so there's your Star 48. If you do that solution with a passive Jupiter gravity assist, you can get to, as a reference, and you can do the math, well, maybe not, because it will slow down further, 27 years to about 200 AU. Okay? So that's number one. Remember this number. Next one is Rendezvous with Rama, essentially. There's another engineering detail there. We need a heat shield, right? Luckily, we are developing heat shields that will actually pull it off, we hope. Launching next year, so we're better, right? This is taken from Hermann Oberth's publication back in 1929. It's actually a pretty nice read for scientists. So I urge you to go online and find it. I'm sure it's out there. Otherwise, I can send you a copy of the translated version. But he looked at it. He had a Gedanken experiment where he put an astronaut with a rocket with a fixed amount of fuel on an asteroid, and asked the reader, how would this astronaut get to the distant star the fastest? And the right answer was that astronaut would have to wait for about 2 centuries until he was in the position to fall into the sun's gravity well, and then he would fire the engine. And then that would be the fastest way to get there. Anyway, if you crank in the numbers, it's pretty simple. For 1,000 AU within 50 years, you need a delta V of about 15 kilometers per second at 4 RS, perihelion burn. Okay? Or if you go even lower, that is about 10.3 kilometers per second perihelion burn. Today, the Star 48, we can cream out about 4 kilometers per second. So that's where we're at. Heat shield. This here is a picture of the Parker Solar Probe back home in building 28. The heat shield sits on top here, and the entire probe is in shadow behind us. What is not included in these mass estimate is all the structural support, all the cooling systems that go with it. So it's kind of a counterintuitive way of doing a mission, actually. Are you diving into the sun to get out to extremely cold conditions in outer space? I mean, but that's what we're talking about. That's the big trade-off here. The payoff could be huge. So anyway, perihelion burn of about 2 RS, roughly about 900 kilograms. If you do go out to about 3 or 3.5, it's up to 550 kilograms, or down to. Do the calculations. So for at 3.5 RS, you reach an asymptotic speed of about 8.3 AU per year, and that's 39 years to 200 AU. If you do like Solar Probe today, which is about 9.5 RS perihelion burn, that goes down to 6.7 AU per year. And if you look at how you're actually climbing out of the gravitational well, that will take you about 47 years to get to 200 AU. So currently, it's not really much better than a passive JGA, Jupiter Gravity Assist. Okay, just a quick summary of mass, power, data, and propulsion here. So again, we base it on a 450 kilogram New Horizons spacecraft. Payload not to exceed is about 40 kilograms. New Horizons with 30 kilograms payload. So we have a chance here. Heat shield, as I said, up to 900 kilograms. The power, best choice today is the general purpose RTGs. We have flown them. We know they work. Ulysses, Galileo, Cassini, New Horizons. For example, the multi-100-watt RTG on Voyager, it still has 170 watts worth of life in it after more than 40 years and some months, right? Then we have the RTGs. They do require lifetime extensions, and that's ongoing. Communication, there's been discussions about a Ka band, which is proven, and we know it works. It's 160 bits per second. It's not giving you much, but you have time to download it, right? And it has very benign pointing requirements. It's a safe, low-risk option to go with. Laser, I'd love to have this rate, which is, I think, is quoted for 10 or 100 AU. I can't remember. But the pointing requirements are insane there, of course. And then propulsion, we're assuming a launch vehicle, as I said, solid rocket, versus the solar electric, radioisotope electric, and nuclear electric. If you look at those, the current TRL and the mass to power ratios, it is nowhere near yet where they need to be, of course. So our best option today is the Star 48 stacked on top of this big vehicle. All right. Two last slide. Next step, we need to conduct a study team. There are other study teams out there. We need to get serious about this, I think. Phase 1. So this will, as Mark Millis points out, this will be all under the Act 1. So of this first study, we propose a feasibility and a trade-off study on the existing technologies. As I mentioned, the Oberth versus the Jupiter Gravity Assist. Followed by other phases where we do a detailed risk analysis. We put the roadmap down of how we want to do it, do strategic analysis of investment and stuff like this. This needs to get into the decadal midterm reports as soon as possible. It's already mentioned in the heliophysics decadal, but we need to get it into the planetary as well if we need to have traction on this. Talked about the RTGs, and of course we need to go international and seek continuing support around the world for this. Somewhat philosophical concluding remarks. Last slide. Incessant obsolescence postulate. Thank you for that term, Mark. I've never really heard about it before, but basically means when do we really go, right? And in essence, 100 years from now, we will still ask that same question. But yet, that has never really inhibited us from doing exploration. So that question is kind of obsolete. So I really resonate with Mark's conclusion there. So I do think Interstellar Precursor Probe, it's time to really get serious about it. I mean, what can we do today to break that path? It's not to be first. It's because we need to scope out the deepening waters of that ocean that we're setting out on. It's scout. So in conclusion, we do achieve asymptotic speeds today that are twice that of Voyager. We have the heat shield technology. We can optimize it. We can build further on the solar probe results, of course. And also, very underestimated, we need this precursor to also push that programmatic transformation that is needed to support these multi-generational missions. It's funding across administrations. It's reliability requirements and all things like this. So with this, I'm going to take some questions, and I'm done. And you're holding up this. 10 minutes. 10 minutes. I have 10 minutes left. This is only a 15-minute talk. Okay. You owe me one.
When you're talking about the multi-generational programmatic transformation, what about staffing? How do you think you'll be able to persuade new staffers to come on board something that they may never see the results from?
Yeah, that's a very good question. I can't really answer it. The only thing I can say is that we're already doing this today. So I'm leading an instrument development effort for the Jupiter Icy Moon Explorer right now, and in the proposal we were required to put that in. How do you transfer your knowledge to the next generation? So it's already happening. So of course, it's when you grow up as a PI and you push that mission, you have to engage already then your undergraduate and your graduate students, and just from that pool of brains and talents, one individual will rise to the top. That's my theory. But you really need to go down to undergraduate and graduate, and we got to do it if we want to do it. So.
With the payload mass and power levels that you gave, those values, I know there's usually uncertainties with that. What sort of range of uncertainties are that? And there's a part B to this question, and I assume those numbers come from technology readiness, ready to fly type of technologies. If you take that to the next lower technology readiness level, about how much does that reduce? Is there some ballpark numbers you can give me on that?
So let me first see if I understand your question. So the 40 kilograms that I quoted, that's the not to exceed mass of this model payload. Mm-hmm. New Horizons had 29.9 kilograms of payload, did not include all the things we want to include. So if you rack it up and compare it to other missions like Ulysses and others, we're still way over. So rather, the 40 kilograms is a target, and we're not there yet. But I say within the next 10 years, we will see those developments coming down to that number for that required payload. Does that answer your question?
Yeah, that kind of gives me an idea of what sort of
it's
margin
hard. It's
there
hard
is.
to get to 40
Yeah.
kilograms. That's
Okay.
it. Yeah.
Thank you.
Yeah.
With all of these possible deep space missions that are, an exploratory one to see how deep the ocean is, and then some further ones and some big telescopes, we really don't have that much plutonium for the heat generators hanging around. Is there do you have a solution or a suggestion? Because
to power sources? No, I don't. I think we've seen an increase in the decades, and that's a lot thanks to Ralph McNutt. Actually, he's really been pushing for this production to go up. There's an increasing amount out there. It's not a lot. It will I can carry it in my hand, which means it's tiny, but I would still put my bet on that for the moment for energy.
Dawn spacecraft using ion drive has now demonstrated delta V's, I believe, greater than the launch vehicle that was used to launch it, so around 10 kilometers a second. Why would ion drive not be considered for a mission like this?
Quick answer, we would probably include ion thrusters in the trade-off study.
So you're not ruling it out. It's
No,
on the
I'm
table.
not ruling it out. I'm not ruling out. It's been coming online. A lot of Japanese missions have proven it as well. So we're following that. Okay. Anything else? Thanks.